Hello, my name is Ben Benkowski, and I'm going to present a training module on high-resolution site characterizations, pros and cons, data interpretation, and quality control. So where does HRSC, as we call it, fit into the overall process of environmental cleanup? I have a couple of guidelines that I follow. That you need to collect sufficient information to make a remedial decision. Not too much. You're trying to be efficient in this process because the purpose is not to remove all uncertainty. That leads to oversampling and more complicated, harder to understand data sets. For me, it's all about the conceptual site model, the CSM. It should be a dynamic model. It should be revised when you have new data, when you understand better about the lithologies, when you understand better about the contamination distribution. You need to revise your conceptual site model. So with the data you have, can you then make the necessary remedial decisions to clean up the site? If not, what are your data gaps? This can be at the investigation phase or maybe later after a remedy has not been functioning very well. But HRSC is shown to be an efficient way to collect the necessary data, to fill the data gaps, and make that remedial decision. So I've got quite a number of these pros. These are just some of the ones I'm going to cover. The first one, though, that HRSC increases remedy effectiveness by providing a detailed and realistic CSM. You correlate data with stratigraphic and lithologic data, contaminant data. You identify source zones, you understand contaminant mass flux, and you can evaluate plume cores and phaeton transport. It really gives you a more realistic evaluation of what your remedies will be. So one of the things that people talk about as that it's the cost of this additional characterization. It's going to cost more money than you have at the time. But from our perspective, it's money well spent. You can pay a little more now to avoid paying a lot more later after your remedy hasn't functioned properly. Better to know where all those little source areas are and factor that into your decisions. So we have a part of our purpose is to have what we call a green remediation. That is to say, one that has a smaller footprint, that's not, wasteful with our resources. So we think that being right about the site characterization is a step towards a green or environmentally friendly remedy. And then that allows you to make targeted remedies because you know the sites better than you would have without the HRSC. It's very flexible. These technologies are very mobile. You can use them at temporary locations as opposed to a permanent monitoring well. And you get a really high density of data. Borehole geophysical logs have continuous readings. Soil and rock cores give you a very great density of data sampling to understand what's going on there. It's reasonably cost effective as well because the field efforts last usually in weeks, not years or months. The equipment is portable and the field crews are generally small. You don't need a whole army of people to go and collect this information. And as the years have progressed, the technology has advanced. It's come a long way from collecting data by hand. Now it's all done with computers, and you have much greater data density. It's much better to transmit into computer simulations and graphics. You avoid errors in data recording and transcription. And as new information is available, new technologies, better understanding of a particular site process, then the ideas can be upgraded. So because it's all electronic these days, it's easier to manipulate. It's easier to organize, and then turn into 3- and 4-dimensional visualizations. Because once you get the 3-dimensional framework, then you can add in things like groundwater monitoring data and watch the change over time. It's really very informative. Makes many people understand a site finally, because not everybody can take a cross-section and visualize it in their head. It reduces the uncertainty. That's just more data, not too much more data, but the right amount of data will reduce the uncertainty about what's the nature and extent of the contamination at your site. With this reduced uncertainty, you get a greater certainty of your future actions, your future decisions, and what it's going to cost you. So the scale of the measurement is important relative to the scale of the property being measured. When I first started doing this work, we often, when we were using a drill rig, we collected soil samples on 5-foot intervals. And while that may have been good enough for the geotechnical purposes that most people used drill rigs for in those days, you can miss things that are smaller than a 5-foot interval easily that could cause great trouble, could cause great uncertainty in how much mass there is in the subsurface, or where that clay layer is that has all the contamination in it. But I had to think about this a bit, but there are some drawbacks by having high-resolution site characterization. Not everybody is familiar with this technology. There are all sorts of different things that we've talked about and are talking about over these 2 days here. And people don't always understand how they all fit together and tell the site's story. So you have to be careful about who your audience is, because you may need to educate them about what data and what types of investigation you're using and how it all goes together. But not everybody will need to know every detail. You'll lose your audience. You'll not communicate effectively. So know your audience. Don't overwhelm them. It's very useful, but there are some drawbacks. It's not going to give you all the answers all the time. Like right now, we don't really understand back diffusion rates, and that makes a big difference on the duration of groundwater problems. Some chemistry information, you really have to have a permanent monitor well that's properly developed to get a representative sample. And sometimes you just can't, the technology doesn't work. You can't direct push in a rocky environment. Even with there's, bold, loose, partially weathered rock, you just can't get through it. So you just have to understand the limitations. Well, and then there's the human nature part of it, where some people just like the status quo and are able to keep, they prefer to keep going the same way they've always gone. But that's not really a recipe for success. You need to work with folks and have them understand that keep going down the same old path will just end up with an incomplete understanding of what's going on. And there are more efficient, more cost-effective ways of solving your environmental problems. So one of the things about having high resolution data is then how do you interpret that for the other members of the team and your management and the public that are involved in understanding it. Certainly we see as the practitioners the benefit for developing a more realistic conceptual site model. Well, all this matches up well with the data density, and it improves your communication and your outreach abilities. And sometimes just two-dimensional presentations like cross-sections just can't tell the whole story of the site. These are three-dimensional problems, sometimes four-dimensional through time. You may have that much information, but just cross-sections or maps, two-dimensional maps, sometimes just don't tell the story effectively. However, you just can't let the computer do all the work, because it interpolates information. And you shouldn't have blind acceptance. It's really machine learning, not necessarily informed by your years of understanding of what's going on and what's the geology like and what's the groundwater flow like. It's really, you just can't let it go off and then just trust it, implicitly. So you have to make sure that the information that goes in is valid coming out. You don't want to output garbage. You need to know what you're doing. Just don't trust entirely the algorithms or the models. So this is a bit of a cartoon where it talks about a source zone where there are 4 DNAPL layers, what the profile is for those source areas, and then how it might be observed. That's a two-dimensional image. Right? And then how that might be projected onto a cross-section with 4 different vertical profiles on it. And this really is a stepping off point to transitioning from a two-dimensional cross-section to a series of transects which show the plume in 3 dimensions and your lithology information. So I'm going to walk through a series of slides here. So first you have, this is your source up here by this A, and you've got 3 rows of field data collection points vertically. And you get certain information from each one of these borings or direct push locations or sonic drilling the samples and collecting those samples. So you arrange your field investigation to develop these transects, because that's how you're going to end up with this high resolution information. That allows you then to take your lithology data and apply that in this three-dimensional grid. So you can know where the lower hydraulic conductivity values are, and because that helps control your groundwater flow. So you get those from cone penetrometer logs, or you could get those from actual soil corings that you've identified the lithologies on. But that's a whole, that in itself is a whole data set that needs to be understood and is better understood in 3 dimensions. Once you get your transects laid out, your lithology information put on them, then you can overlay your contaminant concentration information. And in this case, you can see that there is the highest concentration data directly above the clay layer that runs all the way across the transect. You can also project the lower hydraulic conductivity, the clay layer, that's gotten contaminated by matrix diffusion. That's going to be a problem for long-term sources going forward. And then you can see that below this clay, things are really pretty clean. So certainly no source, no very high-level contamination, much deeper. This is another cross-section in that, another transect where you add the data. You see how the lithologies have changed a little bit, but you still get the effect of the high concentration data being basically stopped by the clay layer. And all this will go into your understanding in the 3 dimensions, which is when you put all that together, and then you can highlight the highest of the contamination. And then this gives you a 3-dimensional view of the size of the plume and where it would be associated, to know that this 4th boring in this transect is in the center of the plume, but the 5th one is not, or the sixth one is not. And then by the time you get to this 3rd transect, you really don't have any of the very high concentration DNAPL type source material. Because this is then what you use to then understand the 3-dimensionality of the problem and design your remedial system for whatever it is works for this kind of a problem. But you really do need this understanding. It's really that way you're not putting in too many random wells in random locations. You're actually putting in the treatment system, in a zone that you have high confidence that it's going to be effective. It's all about reducing your uncertainty and being more efficient and effective in your remedial design and decisions. So here's an example of a 3-dimensional visualization. This is a site that I got to work on up in a state called Kentucky, about halfway to Chicago from where we work. But the people, the Battelle Institute devised a scheme where they could understand the distribution of the DNAPL based upon a potential indicator. So the yellow and the green are the highest probabilities, essentially. It's not exactly like a probability, but more lines of evidence that added up to look like DNAPL. But you can see that underneath this chemical plant, there were quite a number of large areas of DNAPL. And interestingly enough, this blue line here is the shoreline, and some of this NAPL does extend offshore. And also over here you see the different lithology layers that can be, projected into the middle here so you can see the lithology and how it's tied to the DNAPL distribution. And all this was done electronically. But they thought they'd go one step further. So this is the same three-dimensional model, but actually created with a 3D printer. So this is the representation of the DNAPL beneath the site. So these lithology layers are actually printed as separate layers held together with magnets, and then these blue blobs correspond to the blue shapes on the previous slide. This was great for people understanding the extent of the high levels of contamination at this site. It was very useful, a very useful communication tool. I wouldn't call it cheap, but very useful, and useful also given the overall cost of the project. It was cost effective, I think, in helping us get to final decisions about this site. So there's one thing that, how do you do quality control measures when you're doing high resolution site characterization? Well, quality assurance is the broader topic of your whole process of going forward in doing your field investigation and analyzing your data and then looking at the results. But quality control really narrows it down to specific activities such as sampling, analytical and data collection procedures. So I've got a few slides here where utilizing quality control in high res is a process accomplished through a series of additional samples or data sets collected with the express purpose of identifying how accurate the first set of samples or data is. This increases the confidence in the quality of the procedures used and the quality of the data collected. For example, you can have field blanks. If you're going to be using a gas chromatogram in the field to analyze groundwater samples or surface water samples, then you would want to run a field blank to make sure that the equipment is functioning properly, that it's clean, and that it shows that it's clean, so that you're not getting any contamination in the environment nearby. When you're using screening tools such as a FID or a PID, those pieces of equipment have calibration procedures to follow. You get calibration gas, and it's supposed to read at a certain value, and that's how you know. That's a quality control step about how you know that the information you're going to collect, say if you're doing a membrane interface probe that has an FID reader or FID analytical step, then you'll have confidence that that data is properly collected, that it is of high quality. So field duplicates, Officially it's a duplicate sample collected by the same team at the same time in the same place. But it's kind of a different thing to think about it for high resolution. If you're running a geophysical log, you might run a duplicate section of the borehole again and cross-check the results. If you're using a membrane interface probe, you shouldn't go back down the same hole, but offset by 10 or 20 centimeters and run the section again over a duplicate depth range. Then you can compare the results and make sure that, they may not be exactly the same because you've offset, by a small distance, but you should get general agreement for a duplicate location if you're only moved over 20 centimeters. So that's the end of my presentation about the pros and cons of high resolution site characterization, mostly the pros, the advantages of using this high density data in three-dimensional presentations as better communication tools of what you know, but you need to tell other folks. And then some quality control procedures about how to make sure you've got confidence in your data. There are about 8 other slides. There were some additional information I just don't have time for or time to cover. So those are after this. And with that, Shay Wen Ti.